a lot of fun, which means we didn't cover as many slides. And it's okay to do that today. So if you feel like you don't want to get overwhelmed, ask questions. That's a good way. Otherwise, I'll go. And I can skip some steps. It doesn't affect my understanding. But this is a class about your understanding. So, and the question and answer were on the video. So when you go there, you'll learn something. Okay, right here. We're talking about corrosion, so it's a little bit of a shift here. But you know, it said processing and application. The idea of talking about corrosion is when you make a component, not only it has to be strong enough, it also has to be fit for service. And we talk about composite tanks. We talked about plastic deteriorating because of oxygen, because we didn't talk a whole lot about UV light, but the ski binder thing I brought was an example of that. So we're going to finish up the topic of corrosion today, both from the standpoint of what is happening with steel, with aluminum, with copper, and then we'll start touching on what we can do about it. And there's going to be a little bit more on what we can do in the next lecture, especially if you guys ask questions. So steel, we ended up last time talking about this tank, underground storage tank, and there was a lot of really good discussion in class talking about it's buried in dirt. So that dirt is typically not homogeneous. In some area, maybe you have a little bit of sand. In some area, maybe you have a little bit of organic soil. It was mostly clay. So just that difference in the soil properties is a reason for having the corrosion localized in some areas than on others. So there wasn't any cathodic protection in this tank. There should have been. But if it had been buried, say, in sand and kept dry, it would definitely not have the holes, because with a thick wall, it was about 3/8 of an inch thick, so almost 10 millimeters. So it would have survived 100 years if it was in sand that is not wet for most of the time. The weight of the tank was still about the same, so the problem was the localization of the corrosion, and we'll talk about that. But decide to bring in a little bit more of the engineering here. We're going to be using steel, and there was a discussion, maybe it was, I think it was last time, about using sacrificial thickness of steel on piles, for example. So if you bury big beams in the ground, you drive them all the way to the rock, and that's what's going to be the foundation for a building, for example. Sometimes you don't really provide corrosion protection if you put a paint. The paint will get destroyed when you drive through the big rocks and the dirt. You could put galvanizing, but it has a pretty substantial cost associated with it. And in some cases, the galvanizing is not as effective in soil. So you start thinking about, okay, what happens if the piece of steel is not protected against corrosion? And the one number that I think would be good for you to keep in mind is the submerged condition. So in potable water, if you have steel that's corroding, you lose approximately 0.004 of an inch or 100 micrometers per year of exposure. So yeah, if you're building a dock or a little bit of a structure for swimming or anything like that on a lake, and you decide you're going to be using 1/4 inch, so 250 micrometers, then you're good for 2,500. I don't know. You're losing 100 micrometer a year, so 4,000 of an inch, and you start with 1/4. So you don't have it forever. You know, it's going to corrode, it's going to be a problem, and we're going to talk about the methods to protect for that. So From that number here, about, if you want to lose 0.2, it's 50 years. Actually, it's a substantial time. But the piece of information there is you're assuming homogeneous thickness loss, which really almost never happens. So the case of getting perforation with something that's very thick, a 1/4 inch thick, would be half that 50-year life, so about 25 years. You had something really thick, a 1/4 inch, and you perforated through it. So it's not useful anymore. And that's about what a lot of people would do. Use relatively thick steel, you put paint, but the paint literally lasts just a couple years, and then after that you have the normal degradation taking place. So that's where you put your boat when you become very successful, all of you. If you are in, so if we go up the table here and that it is not submerged in water, you can have a condition, so the splash zone is where the tide goes up and down by the ocean. I think we can all agree there's just a lot more going on there. There's activity essentially to remove that scale, the condition change, so you lose the protective layer, you lose the scale that's being built on the piece, and therefore your corrosion rate is the highest. At that point here, you can lose up in average up to 3/4 of an inch in 50 years. Yes?
Is the scale, what's the scale made of? Is it oxide or is it
there are
micro?
hydroxides and oxides, and there's a very complex chemistry there. Yeah.
And then natural, like organic life as well?
No, so it's typically inorganic. I showed a sample earlier. You have magnetite in there. You have different layer depending the pH you're at and how dry or wet the environment is. And the chemistry, so there are some steels that are called weathering steel that form a different oxide that is more stable on the surface. So there's 2 or 3 possibilities. But here it's really to give you just a general sense. If you have a working tool, like a shovel that you leave outside, that's going to be in rain sometime, but not all the time. If you look at the steady rate here, we are significantly less, so it could be about 1/10 of what happens if it's submerged all the time, but in certain condition, it could be just half, so very close to what happens in submerged water. Now, the way perhaps you can remember that the value for in submerged condition is constant is it's driven by the supply of oxygen through the water. And you always have a certain amount of oxygen in aerated water, and that has to diffuse in and out of the surface where you're reacting. So what we're always saying is, I got the piece of steel, and it's not connected to anything else. It's right there in the water. So let's say we have a lot of water here. So there's always going to be some oxygen coming from the surface. There's going to be some plants there that may be generating oxygen, I'm sorry. And then when it gets to the surface, it causes a reaction, and you have the anode cathode effect, and you just start losing thickness. So when the oxygen gets close, you have a diffusion film that is what is controlling the rate. And if you're buried in soil, we're talking about these rates are essentially for wet soil. If it's really dry, nothing's happening there. But for wet soil, it's very similar to what happens here, because you also are limited by the oxygen. So if you happen to have a portion of the soil that doesn't have oxygen, then you can't really corrode. So there's going to be a lot of variation, and that's what we saw in that tank. The clay would just stop everything from moving. Any question on this? Because this is out of the ASM handbook and some standards. I had to put it together for an engineering project because the office I was working in, we didn't have anything. We didn't have any guideline on what to decide, what to recommend a customer. If they say, well, you know, my contractor doesn't have the time, we're talking like here, we're out on a oil and gas platform, we're out at a special, you know, exploration site, and we're not going to go and start applying corrosion protection. So you're going to send us material that we know is going to last the useful life that we're looking for. We're asking questions, so I think we got it right. Working as a team on that. But then after the class, the question, student came up and say, well, you know, why did they put in the aluminum in the first place? Okay, so I mentioned one thing, which is to be able to form it to shape and keep that shape. And then the other reason that now perhaps you can understand better from what we discussed is we don't want the oxygen to go into the system, because this is a hot water heating system, and it has cast iron or metallic burners where you circulate the water, boilers, and if there is any constant supply of oxygen in that piece of steel that's used at very high temperature, it's going to corrode. So the water is going to be rusty, the pumps are going to break, and eventually you'll leak or have to replace that important component. So it's not a problem if you're using a steel pipe, because oxygen doesn't go through steel very easily. But when you move to the plastic, you have a lot of diffusion of oxygen through the plastic wall that the aluminum layer acts as a barrier for. So that was the original reason why they put it in. It looks like it wasn't clear, so clarifying that. Okay, now what are we going to do? For steel, one easy thing to do is to move in a region of stability of the oxide. And I'm only going to mention the one that I'm most familiar with is putting the steel in concrete. So you raise the pH, and then all of a sudden the oxide that you form on the surface of the steel is stable. It becomes a little bit like aluminum. So it's self-protected. Now, there are other ways to reach that level of protection. If you have a heating system on the inside, you can put inhibitors that are going to bring you to a condition where you don't have the formation of an unstable oxide. So in this case, it essentially is working on the electrolyte. You change the environment. So you can only do that in certain conditions. So that's why we talked about concrete. And then the example of a closed loop water system, some industrial cooling systems are made exactly that way. So that's the analogy here. So on the aluminum, you have stability. Yes?
How can concrete have a pH?
Okay, very good. The question is about the pH of concrete. I'm not a concrete expert. What I'll say is the cement itself is it's a basic material, so it's not caustic, but it's in that category. So when you mix that with water and aggregate, you have a high pH. So it's essentially by the composition of the cement, and then you can vary it. So you can have grouts that are going to have a much higher pH than the regular concrete to increase that protection. Thank you. So aluminum here in the zone B, we have the stable oxide of aluminum, the alumina that will essentially resist the penetration of more oxygen, and it remains stable on the surface. So if you scratch aluminum, a lot of times it will remake that layer very quickly, and you don't have too much trouble. Now, there are exceptions. So if you put aluminum in concrete, now all of a sudden you can see you're becoming in another phase of aluminum. It's AlO2, and that is going to corrode. It's not going to be stable, and it's happened on a number of projects, people using aluminum for railings, things like that. and after a while they have a lot of localized corrosion where it meets with the concrete. It does depend a little bit on the amount that the pH of that grout. If it's close to 10, you know, it's all about your potential here. So if you're far enough from the higher pH, if you're close to 8, 9, 10, you may be okay. But there is a limit, and unfortunately, a lot of people find after the fact. There was somebody in class 2 years ago that was really experimenting, building. I don't know exactly what he was building, but he was using aluminum containers with acids, and he will lose his containers and really wonder what it was. But here we have the answer, that you don't have the stability at that point, and therefore you're going to corrode if you use an acid in an aluminum container. Yes?
People always talk about how aluminum oxide is super stable and so impermeable.
Yeah.
Like, so to me it's like, oh, how big of a problem is corrosion in aluminum really? Like, if the oxide's so stable. But like, I know in some applications, it can be really dangerous. You have deep corrosion of the oxide, but I don't know why that happened.
Very good. So the question was exactly what I was trying to answer, but I didn't explain it well. So aluminum generally, it doesn't have a corrosion issue, because normally it's in zone B here on the screen. It's on the zone of stability of that alumina layer. But if the x-axis here is the pH, if you move out of pH about 3 to 9, you lose that stability. It's not anymore the alumina that is the most stable oxide, and those other oxides don't form a very good surface that is protecting against corrosion anymore. So it's not isolating the substrate, and in those conditions you have accelerated corrosion. So, I mean, and simply put, you don't have a problem with aluminum because you use it in ambient condition where pH is around 7, maybe up to 9 for certain waters. But it's really when you fall outside of that region and all of a sudden things really corrode fast. So, corroding fast, and I brought a few pieces for you guys to look at. Not yeah. So, we start with copper, who has a natural protective oxide on the surface, but as you can see, it's not always there. There's no thickness left here. This is the original thickness of something like this, and there are other places probably that has the same effect. So to start corroding copper, you break down that protective layer on the surface. What you can see here essentially look like drilled holes. So there was a little bit of a deposit here. There was a big buildup. So that's the outside of that location is built up just like you see on the image. And if you're not really familiar with what's happening, when you look at this, you could say, well, maybe this is insulation products that got caught into the system during installation. But they had reported leaks. This was a very big, high occupancy rate building. The system was only about 10 years old. It should have lasted much longer. But yeah, so when I went to the site, started looking at it, started really thinking, well, maybe there is an issue of corrosion here. It wasn't leaking. And the interesting thing there about not leaking is when the water from the inside was going through that pit to the external surface, you were essentially evaporating, or you were making distillation of the water, and the deposits, the salts from the water, were able to clot that point. Now, is that permanent? No. It's going to form. It's going to be stable, but it's a very it's a very short-term solution. It didn't adhere all the time, So in that case, if you just brush off the outside to clean it up, then all of a sudden you start leaking again. So I mentioned that it was a lot of use. So there were deposits here inside the line from a lot of usage, a big flow rate. And that was one of the triggers. And I say triggers because there's more than one in this particular case of why this plumbing deteriorated very quickly. It didn't have much to do with the quality of the copper. So this is something that happens a lot. I mentioned on Friday I had a call from Association of Homeowners in Boston. Apparently it is the most expensive homes. So they didn't accept that we were not going to help them. So we'll still have to do some consulting for them on that. But the first reaction that a lot of homeowners will have is, oh, this is bad pipe. You know, it broke right through it. Well, maybe, but there are other factors that you have to look at to explain why this happened. And in this case, definitely the water chemistry, the usage, and the deposits that were visible inside the line were part of the triggers. Any question on pitting corrosion or this example? Yes?
So what property of your water would be most dangerous? Right?
Very good question. So what is in the water that affects the corrosion, I believe is the question. A common way to look at it is to look at the Langelier index. And there are other more sophisticated ways, but let's say we have Langelier. It's a relatively simple equation. You can look it up that takes into account pH. It's going to take into account the alkalinity. Chlorides in there. We have temperature. There's another one. Oh, dissolved solid is an important. And you want to double check, so I'm just going to say plus, but. So it is known, I guess is hopefully part of the answer. It does require you to extract the sample and send it to the lab to get a lot of analysis. But one mistake that a lot of mechanical engineers that spent their life designing plumbing system keep forgetting is they'll focus on this one and say, oh, this water must have too many chlorides, or there's hardness. So it may not be chloride here. I think the standard formula is the hardness as CaCO2. The chloride is just a trigger, but essentially if you can control your hardness, your pH, your alkalinity, your dissolved solid, your temperature, you can find a way that instead of forming a natural oxide on the aluminum or a protective oxide on the steel, you form a layer from the water that is a calcium carbonate base that is high pH and essentially neutralize the corrosion. So that's a way that's used a lot. And in municipality, you have a lot of requirements to make the water potable, but there's also a need to make sure that it doesn't affect the plumbing system. And unfortunately, making sure that it meets health requirements has been more established, more controlled, and making sure that it doesn't affect metallic piping systems. It's a great question. Thank you. So other examples, cooling systems. You can see on the left, it's a steel pipe, and you have what we call turbocool in it. So you can't see through that pipe. There's too many things. It doesn't mean it doesn't carry water any longer, but it is harder to carry that water. So it forms an extra resistance. And under those tubercle, we can have this corrosion effect because the environment in terms of oxygen and chemistry is very different. So when you start seeing this on the inside, typically it also means that you have localized corrosion or pitting of the pipe. So it's not good. And the way to avoid it is a bunch of inhibitors. Some are going to be to protect the steel and some to prevent the growth of these products inside the line. But we see this in very fancy hotels. We've seen it even in potable water in casinos. The problem, one challenge with casinos is they tend to be built all at the same time. You know, when there's a boom in the economy, they go and build and then they stop. So for getting quality contracted work done, it's a challenge when they're trying to make 5 casinos in a city that there wasn't any, work for the past couple of years. So getting local contractors is a process. The copper pipe, I'm showing it because that's an example of corrosion erosion. What you can see is on the outside curb, it wasn't cut perfectly, but I think you can see right here on the upper right, it's very, very thin wall at this point. And it's on the outside of the curb, which brings me to a topic I would like you guys to remember, is this internal corrosion in plumbing system is very dependent on your flow rate. So if your flow rate is high for copper, there's a threshold, and it's not much higher than what we use. So one reason for having, let's say, a 1/2 inch or a 3/4 inch line is you don't want the water to flow through fast, so it causes the erosion and the damage to the protective film. So what happened in that elbow, it was just too fast with the circulation, the vortex effect in the corner, that it lost thickness. And you can see on the inside wall, it's got plenty of thickness, so it really affected preferentially the outside.
And that's all just physical weathering, right? Or is it chemical as well?
So as far as the erosion in this case, there are always some solids on the surface. So when we call it erosion, there is some interaction with particles. This was a cooling system that went underground, so there was a well. And even though they had filters, there's always some particles involved there. So think about that the particles are going to come and scratch your protective film. And if they do it at a rate faster than you can regenerate it, then that's really where you have a problem. And for the image to the left about the steel, again, with different flow rates during service, you can minimize the risk of forming these tubercles. So you can keep the composition more homogeneous if you are above a certain speed. So now maybe you're not as interested to design a plumbing system because you have a minimum and a maximum, right? So you really are having to do your homework based on experience of similar use as to what is acceptable to control corrosion. You cannot eliminate it. As soon as you take that piece of copper and put water in it, there are reactions taking place. You just need to make sure that they don't affect the service life, if you can. Okay, well, stainless steel. Just by the name, it says that it's not stain-free, right? It can corrode. And I don't think I brought really a drastic image of corrosion of stainless. This is because of the topic of today. I can also say that if you put stainless steel in the ground, in soil, there will be conditions going to corrode just as fast, if not a little faster, than carbon steel. And those conditions are when you lose the stability of that same surface passive layer. So I guess one simple way to look at it, if you think of titanium, aluminum, and copper, they look good naturally, right? You put a little water on it and they look fine. They all have a stable protective layer on them. Therefore, they are all at risk for pitting corrosion because you have to perforate through that protective film, and when you do, it's at one spot, and then you have more risk of pitting than you do on a piece of steel. You only get really bad pitting on steel if there's a specific condition there that you have coal tar or a different soil condition like we saw with the tank. So on the case of stainless, this was a very fancy home that we were asked to consult on. It was built, and within literally 2 months, instead of being super nice finish, it looked like this on the outside. So quite terrible from an aesthetic standpoint. Be fine from a structural standpoint, and what they were looking for was something like this. So I'll pass it around. This one is actually not the original. So this is what comes out the mill, and that wouldn't corrode. This is what we did as a refurbish or repair. This was another repair that didn't work, and this is exactly as installed. Okay, so stainless. It means that it has the natural protective layer, but by the moment you break that layer, now all of a sudden you start having pitting. It's going to have that bleeding rust effect. They were not expecting this. They had another project before with stainless steel that succeeded in the same area. This was at the Hamptons in New York, fancy homes. Okay, what did we do? Did a little science here. So you can see all these marks were just to be sure we can tell exactly where we're looking. Because we decided to do microscopy in the area where it looks like the source of the rust was, which means you have to go and magnify quite a bit because you can see. So this is a small magnification here of the same area, and then zooming in a lot deeper here on the electron microscope, where you see our sand particles. So what I'm looking at here, here, and here are sand particles. So yes. We did run the question was, how do we know it's sand? We ran the chemical analysis under the scanning electron microscope. It's very, very useful when you don't know what's going on. So it was silica, which is very common. So blasted so strong that the particles got into the surface and really created a pit. The reason they wanted the sandblasting was to get that matte finish, which is, more popular these days than, I think it's in the 80s, everything had to be very shiny. Now it's got to be matte. Who knows what's the next step? Shiny again. So it's had to look that way, and the process parameters, they didn't even think of it. It's stainless. I can do whatever I want with it. No, you can't. And the problem is, as soon as you start pitting that stainless steel, it's very hard to get it back because now you created holes. And so you can brush up the rust, but you'll have a problem again. So we went on and did a lot of ways to try to solve their problem in this particular case. And at the end of the day, they had to blast it. They had to, and it was most of it. There was a lot of windows, so they had to block the windows, blast, and put a lacquer on the surface. And what the lacquer does, it prevents the chloride from coming through the surface. It doesn't block the oxygen and the water, so moisture will go through just a little lacquer. But the idea is if we keep the chlorides out, I forgot to say this was by the ocean, then you don't start that pitting corrosion again. So chloride really had a big role in growing the corrosion pit. And I have another example that's a little bit alike. We're looking at it here. columns in airports. This was the Miami Beach airport. So that was my first time I saw the beach over there on this project. So it looks really nice from far. When you get close, you see those patterns. So it's embossed as far as the finish. It's stainless steel, and then it's brushed. And they have a good way of doing this. You can't brush with a steel brush. In this case, it has to be a stainless or a nickel brush because you're going to contaminate your surface if you use a steel brush. They had problems. You can see three conditions here. The top left is the original surface. The bottom is what happened and why the owners complain. No, it's the repair. This one is the repair. And the upper right is a corroded one. The order is not perfect here. So it's a corroded one, and you can see the small pit. You see the little black spot? This is where the rust was starting from. So what happened? They use an acid cleaner. This is like the pickup and drop-off area. They use a big acid cleaner because they were just finishing the tiles. And it wasn't windy that day, so there's essentially been a lot of very acidic environment staying in that region to cause the problem. They did a further analysis. They said what happened is, oh, we used this cleaner. It caused everything to rust. Let's get the rust off. So instead of going and hiring a metallurgist, or maybe they had one, but not a good one. Actually, I know they had a metallurgist. So you say, I'm going to remove the rust and move on because that's the problem, right? But the big problem on the project was even after the best cleaning they could do, they still had those holes, and nobody told them. But really, what happened after, and that's when we got called in, started rusting again. Okay, so this second time that it rusted, it wasn't the cleaner, right? It's just like we discussed, it was these little holes that were in there, and the chloride environment, close to the beach. A lot of moisture coming in to, reestablish the process. So if we had been called after the first cleaning, you just spray a lacquer and you're done. It'll continue to look exactly the same. But so they went through the most labor-intense part, which was to sand off all those surfaces, but didn't do the extra step of protecting against future attack. And we see that all the time. It's on small boats, like sales boats. You can have all sorts of nice finishes in there, and they'll survive if you are willing to periodically maintain them with that soft, dissolvable lacquer. So what happens with the lacquer is you do want to replace it. So it will dissolve in alcohol. So when you say, oh, I'm starting to see a few rust spots, so now you go and remove the old one and you put a new one and you're good for another few years. So that's it's kind of the situation you have to go through if pitting is a risk for you. Now I'm showing a table of chloride level as opposed to temperature for forming pits in stainless steel. It's a very useful table if you're trying to explain to a client or the owner of a facility where he's at and what he could do. So there's an interesting thing in this chart, which is one of the most common grade of stainless steel is not even written. So stainless steel 304 is very, very common, but it doesn't make it into that one chart. So it's not good. Okay, it's not good in the presence of chlorides. It will eventually pit and look awful. The first one here in the series is stainless steel 316. That is a little bit of a default if you know you're going to have somewhat of environment with a little bit of chlorides, not a whole lot of chloride. But you can see in this chart, that you can increase the ability to take chlorides by an order of magnitude when you change your grade of stainless steel. And that's really where it's significant. So we can be here, you and I, complaining that stainless steel not perfect, but if I have something to build that's not that big, and I am able to afford, greater alloying content into my stainless steel, then I don't have to worry about it. The problem in terms of the concentration of chlorides that you can see at the ocean is you have what's in the salt water, but when the mist is condensing on structures, you can actually go to greater concentrations. And that is the reason why people wash their boats and wash their homes on the ocean, because otherwise you keep building up and keep having more and more chlorides on the surface. Yes?
What specifically about chlorides makes skin steel vulnerable to them?
Oh, the effect of chloride is on the stability of the protective layer. Yep. It doesn't directly collect the iron and alloy with it, but it's changing it's a little bit like a catalyst into this process. It's part of what it is. We use it for salt for cars, and that may bring us to the next topic, actually. So if we I mentioned that you don't want to use regular steel as tools to work on stainless. So what you see, this is a very expensive pressure vessel that's got rust on it. And the customer called in saying, hey, this is not supposed to happen. And the only thing they did at the shop is they were using regular chains to lift it. So it smeared some regular steel on the surface, and that's what caused it to rust. And there's a little test. You see it becomes pink. You put a little solution. You clean it off first. You put a little solution, and you look to see if there is any native iron that is not combined with the chrome or the nickel. So you're able to quickly identify that it's not a pinning problem. Yes?
Does it have to be do your tools have to be the same grade of stainless, or just is there some nickel and chromium there it helps?
Good questions. The question was, do you need the same grade? No. You have to be careful with grades if they're going to be in contact all the time. But as far as just a short-term use here, I would go for better than equal, just because you don't know all the things that you're going to be handling, all the grades that you're going to be handling. But the idea here is not to be able, and it doesn't have a huge long-term consequence. It just doesn't look good when you send a multi-million-dollar piece of equipment that looks rusty before it starts being used.
But it's not actually rusty.
It is actual rust, but it's not rusting through the thickness. Yeah, it's the extra layer. Now, if you are in a somewhat limiting environment, so this is going to be exposed to chloride, it could just keep triggering the reaction and continue, actually. So it's not just aesthetic in certain conditions. Yes. Okay, so how are we going to avoid corrosion? We're engineers. We can understand the problems, but we also want solutions, right? So the first thing is it'd be great to put a paint. And I showed the example of the storage drive tunnel where you can see they tried it on. They put paint twice. There's an old layer, there's another layer. And the issue with paint on steel is you don't only need to protect against the chloride, you need to protect against moisture and oxygen. And that's very hard because it's an organic coating. So over time, it will get through it and start the corrosion. So the idea that you put on a paint that is not going to get through, there are a number of conditions. If it's not raining all the time, then you get kind of the moisture starts getting in, but then it dries back out, and then you're good. You keep going this way, and if you put it thick enough, you may make it. You may, but it's scary. So one way for ships, for example, that are on the water all the time is you really have to use a hard epoxy, so a very dense a coating that's hard to put on, that is not as easy to keep the adherence for because it's stiff, it's very, very dense. That's how you limit the oxygen and the moisture penetration into it. So those hard epoxies can give you a life of the order of 20 years, maybe 15 years in submerged condition, but that's the best you can do. Now, it does go to, you probably learn if you go to the store, oh, this is a zinc primer and all these things. So in that case, what you do is you have little particle of zinc that are going to act as a sacrificial anode if some of them actually touch the part. So you need these particles that you see here to be in contact with the steel, which is not the case in this one. So this one, they did not know what they were doing because they put on a primer without zinc, and then they put a zinc primer on top. The zinc is not touching the steel, so this has no advantageous effect. So it has to be touching electrically, and then it's sharing the electrolytes so you can have the positive effect. The mistakes happen all the time. So I talked about impressed current and the context of pipelines. And we have these in certain locations, and sometimes it's for water pipes, sometimes it's for oil and gas pipes, although the oil and gas tend to be more sophisticated than this. So you have to bond the wire, and I've got these little welds here, to the piece of metal. Let's say it's a water pipe in the ground there. It goes to this port, and here you also have another wire that goes to your anode that you've put into the ground. You connect the two, and you're good. Because the environment is the soil and the moisture, that's the path for the electrolyte, and you made that electrical connection. The reason for having that access hole is you can go in there with a voltmeter and see if everything is working. Am I applying the right voltage still today? No, it went down, so my anode's gone. I need to put more anodes into the ground, or sometimes you could say, well, it's kind of dry, so it's very high resistance, so you actually you didn't really need the anodes for this particular case. So now you go on the day that it's after a big rain to see what's going on. So it's a very complex process, but the idea here is with a little money, a piece of aluminum, a bunch of electrical wire that have to be put on correctly, you can significantly extend the life of your components. And that may be the last one for today.
So you need to have conduction to the anode. And in soil, there's a lot of resistance. So does that mean you're putting that you need to pump more voltage, put more current into the anode?
Yeah, yes, okay, so
it's more costly to have right?
Yeah, so the question's about kind of like what's going to happen, more or less, and I'm going to draw it off. So we have the pipe here, and then we've put on an anode right here. We put this little well that I've shown. It goes to the access port. I connect the two wires. So this is essentially creating a galvanic effect. So physically, this and this is touching electrically. Now I have my ions that are going to be going through the soil from one path to the other. That's how I established that this is going to corrode instead of this one. If I'm able to do, and the way I do that, again, is I do put a coating on this, because otherwise I'll lose my anodes very quickly. So it's a way to protect the surfaces in the areas where there is actually infiltration, because otherwise you'll need too many anodes.
The current's balance, like the current that would be in the wire versus the flux of charge through the...
So, I think I understand the question. There's no power supply here. It's just that this anode has a different potential. It has a different equilibrium potential in the same soil, and that's what makes the driver.
So you're not even applying...
No, you're not applying anything. The variation you can do, you can say this is going to be kind of a carbon anode, it's going to be a permanent anode, and then here you put your rectifier.
That makes sense.
And that's used for the oil and gas pipelines.
That's super long term then.
Yes, and it's not super expensive. It's mostly the setup to get the high power line to get you the power you need for every location that you put these. So the anodes, you don't have any necessity to bring electricity. Eventually, when you guys' generation really makes solar power really, really good, this could just be made with a solar power there. Yes?
As a comment, in Christmas trees, Subsea, they basically put a big block of magnesium on the tree and they use it to balance the weight. So they don't actually have to worry about where their center of gravity is because they're just going to balance it out with cathodic protection.
Yeah, so in seawater, you made a comment about using the magnesium, and if you look at the outboard motor for little boat, big boats, they do have a magnesium anode that you screw on. So it's a very, very simple way when you're in water. You just tag it along, and it's connected electrically. That's is about all we can do. So I do want you to remember there's always an anode and a cathode in corrosion. There are many ways to control corrosion, and it is control. You can't prevent it. You can't say, I'm not going to have any effect with the environment. You just control it. Thank you very much.